Hi, everybody. We're going to get started. So first up today, we have Dion Ho. Dion is a PhD candidate in the Department of Applied Mathematics and Applied Physics, advised by Lamont Research Professor Robert Pincus. He is interested in PDEs, numerics, and their applications to atmospheric radiation. He graduated from Yale NUS College. NUS stands for National University of Singapore with a Bachelor of Science and a major in mathematical, computational, and statistical sciences. In his undergraduate years, he worked with the United Transform Lab to further develop the United Transform Focus method for solving high order PDEs, and separately also researched on the nonlinear Schrodinger equation. Thanks, Dion.
Thanks, Kate. Hello, it's good to be here and to present my research once again. I think many of you have seen my past presentations. So yeah, let's get started. Oh, God. Okay, so yeah, today I'll be talking about my work for the past over 2 years now, actually, on data enhanced two-stream methods. And so just as a brief introduction, what we are interested in calculating is the reflectance and transmittance of sunlight in particular, though I'll say that my research is applicable to more than just sunlight, and radiative transfer in general is of course about long wave as well as the short wave. But today we'll be focused on short wave radiation, so sunlight. So what we are really trying to calculate is this reflectance, which is just the amount of incoming sunlight that is reflected back out into space, and the transmittance, so the percentage ratio of sunlight that is transmitted through the atmosphere, through clouds, to the Earth's surface. So this is generally done using this two-stream, in other words, two-directional model. So you have one equation for the upward flux, one equation for the downward flux. And just evaluating the fluxes at the boundaries will give you your reflectance and transmittance. So this is the most parsimonious scattering model for computing radiative fluxes. And so I emphasize here on the word scattering and the fact that this is a shortwave model, because generally if you're modeling long wave radiation, scattering is considered to be negligible. Well, there's debate on that, but yeah, so usually you will omit the multiple scattering parts if you're focusing on the long wave. So an alternative to the two-stream model, just to give you a sense of what is happening, is a high angular resolution model. And the point here is that you can see my diagram over here. You will basically try and resolve the radiative transfer in more than just the upward and downward direction. You'll try and resolve it in like multiple angles. So you have like polar azimuthal angle, and you try and resolve it in multiple directions. So for climate models, this high angular resolution model is too computationally expensive, hence you use the two-stream, right? And that's where its parsimony is important. However, this model over here provides our ground truth. So when we want to compare the results of a two-stream model, we are basically comparing to this high angular resolution model. Though one thing I would add that in a way, even this model is not so-called like the perfect radiative transfer model, because it is still a plane parallel 1D, column atmosphere model. If you really want to be more sophisticated, you'll use like 3D Monte Carlo calculations and whatnot. But in any case, we stick to the 1D framework. So that's the upshot here. So one thing I really want to emphasize on, and this will become quite important later, is that when we do radiative transfer in a climate model, speed is very, very important, because radiation needs to be resolved at a very high spatial. And by this, I mean the vertical stratification in the atmosphere, vertical layers. Usually you have like 100 per column, 60 to 100, I guess. Horizontal resolution, every single column, right? You map the surface of the Earth, you grid it up. There are like many, many grids. And not to mention the temporal resolution, every time step, you'll try and resolve your radiation. And finally, spectral resolution as well, because you have long wave, short wave, and more than that, you will probably want to split the whole atmosphere into multiple bands. So radiation is, you will be calling the radiation scheme like millions, I don't know, trillions of times. So you really, really need it to be fast. How optimized are we talking about? Well, there are radiation schemes and there are papers on radiation schemes where researchers are talking about trying to minimize the number of exponential terms in the scheme. So we are in a world in which exponential terms are considered expensive. People try to replace them with multiplication. That's how crazy optimized we are trying to get at. So the current analytic approach, and this has been done since at least the 1980s, probably even earlier, is that you assume an angular distribution of the radiation in each atmospheric layer. And if you do this, your flux can then be determined analytically. So you solve everything analytically, compute everything, that's it. You're done, no need for any data. There is some logic to doing this because deep within a cloud, the scattering becomes diffusive, and so the radiation field becomes approximately isotropic. And so basically, the old schemes, the analytic methods, usually you will either assume that your radiation field is isotropic, or you will assume not quite isotropic. There's some nuance, but yeah, so approximately isotropic, or you assume that it is very anisotropic, so it's almost like a delta function. And in both those cases, you can get some nice analytic solutions. Of course, the truth is that, within a cloud, in between the two extremes, this is not, you will probably get some other angular distribution. And the problem also is that even if you can predict perfectly, accurately, the angular distribution throughout the cloud, the resultant expressions may not even be closed form. So it's not just that it's difficult to predict the angular distribution of the radiation field within the cloud. It's also that most angular distributions, you can't even resolve it in some analytic closed form way anyway. And when I say may not be closed form, I actually mean will not, because if I use, so we talk about the multi-angle expression, this is the high angular resolution model. We actually know that the radiative fluxes have this expression over here, where n over here is just, I'm summing over all of the directions that I resolve in, and basically when n tends towards infinity, then you imagine that you resolve everything like next to perfectly, you get convergence, if you will. No need to care too much about the details of the expression. The main point I want to make over here is that this expression over here relies on certain eigenvalues, lambda over here, which are the eigenvalues of a scattering matrix, some very large scattering matrix which scales with the number of angles you use, or streams, actually, in the literature. And these eigenvalues probably have no closed form solution. For those of you who are more math inclined, you think that you have a matrix that's more than 5 by 5, the eigenvalues no longer have a closed form expression. So so from there, we already know that there is no closed form expression for this actually. However, using this same expression, we can show that the radiative fluxes are analytic with respect to the optical parameters. The optical parameters are the input into my radiative transfer solvers, either the two-stream or the multi-stream. And therefore, spline interpolation in general, Taylor series expansions are guaranteed to converge, and you have rapidly decaying errors. So if you don't know what analytic means, don't worry, it doesn't matter. The whole point of it is that your functions are really nice in some, are very, very nice. And so you get convergence guarantees, you get the error decays really fast, and this will have some implications for our methods later on. So I'll be talking about technically three, I split it into two sets of data-driven two-stream methods. One is just spline interpolation, pre-O, traditional, I guess, but I will tell you that this is really tried and true and produce some really good results. And then as more advanced methods, I'll be showing you a method using symbolic regressions, using PySR. I know like many people all use PySR. So hopefully I can show you all something, some interesting things to say about PySR. And then versus symbolic regression versus using a multi-layer neural network. So spline interpolation first. How we do this, somewhat simple where, I mean, if you just see, sure all of you know about splines. So linear splines, you can do it in 2D, you get bilinear, bicubic, and what we are doing is basically a 4D spline, so tetralinear, tetracubic. So what's really nice about using old, more traditional method like splines is that you have some very nice proven mathematical properties that I can leverage, especially since I know about the niceness of my flux functions. In particular, I get uniform convergence that is guaranteed by continuity. I'll show you the implication of that later. And I get fast convergence because of the smoothness of the functions, which are interpolating. And very importantly, remember I talked about how it's very important that you resolve your radiation very quickly. Well, the forward evaluation of a spline, once you, I guess, build the entire spline, it's really fast. Because in general, so how it works, right, if you want to evaluate this, is that you just have to find the correct spline. That's just the most expensive part. Evaluating a cubic polynomial is trivial, it's blisteringly fast. How you find the correct spline is that you just do a binary search. However, in our case, where you will probably want to evaluate like multiple layers simultaneously, you can basically just make the evaluations contiguous. So it's kind of a contiguous memory kind of concept for those of you who are more CS inclined. But you can make use of that to do your evaluations for many layers, many ordered layers really fast. And yeah, so obviously, once you find the correct spline, evaluation is very fast. So using 68,000 data points, it's 20 by 20 by 17 by 10. I will add that we don't have that many features. So actually 68,000 data points is actually not quite a lot of memory, in case you're wondering. I remember I computed it before, it amounts to something like just 5 megabytes. But in any case, if you do that, your cubic spline has less than 1% error, linear spline less than 4%, and of course, if you want to compare to status quo, we are talking about like huge error, basically. And indeed, why our splines can get such low error and percentage error, no less, right? So it's really because of uniform convergence, right? And we know that if we add more and more points, the percentage error will just go down and down and down. You can make it arbitrarily small. This is pretty much guaranteed. Cubic spline works better. That's not a surprise to anyone. However, why we would want to consider linear spline is because of thinking about this in an adaptive sense, where I mean, a priori, we don't know how many data points we need, right? Let's say you want to achieve 1% error linear spline. How many data points do you need? Hard to say. In that case, you can basically make it adaptive, right? You can try and predict. You can do it once, evaluate your error if you have some sort of validation set, I guess, and then add points as you need until you achieve the error that you want. And in that case, that's where linear spline shines, because you see my tiny little schematic over there. Adding points to linear splines is trivial, right? You just add to one point, you won't affect the other splines. Whereas cubic spline, if you add points, you need to reevaluate the whole thing all over again. So linear spline, that's something to consider as a very generalized method, generalized and adaptive method. I will say that one nuance I am sort of skipping over is the distribution of the points. So this is not just, oh, 20 points, linear spacing, everything is great. Some nuance to choosing a distribution of points. I'm not even sure I'm doing it optimally, but yeah, anyway, those details. Uh, oh, okay. Okay, so now talking about symbolic regression and neural networks. show you, yeah, the results. So PySR, what I do is I set my max complexity to 80, which is kind of considered pretty high, but for my hidden layer, and then so just two hidden layers, right? One input layer, output layer, two hidden layers in between. So my NN has 700 hidden variables. And so complexity, because some of you may not be as familiar with the term, um, so x plus y, for example, will have a complexity of 3 because you count x, y, and you count the operator, the plus operator, right? So actually 80 max complexity probably amounts to just half that in the number of variables. So you're just, so in a way, you are comparing probably something like 40 to 700 hidden variables in a way, right? So you can see some of the results. I mean, sure, your neural network, absolute error, pretty small. That's great. Probably can bring it even smaller if I use more hidden variables. Whereas for PySR, you can see that accuracy is not that good, but we are in a way using a much sparser model. I'll follow up on that idea in a bit. One interesting thing I want to point out over here is that there's this idea of, do we use put exponentials in the PySR? Do we allow PySR basically to use exponentials, or do we not? You can see the results are actually quite similar, and the reason for that is actually because we are here making use of the analytic property of our flux functions once again. Because for those of you who know exponentials, if you do a Taylor expansion of an exponential, that Taylor expansion actually converges super polynomially fast. Very, very fast, basically. I will add that so you'll notice that previously for the splines, I talked about percentage error. Now I'm talking about absolute error. The reason for that is because indeed there are certain points where the percentage error can be really bad for both of these methods. And the reason for that is because we do not have a uniform convergence guarantee in these methods, but the spline does. So this is where actually we use the uniform convergence property to get like really nice errors, really small errors everywhere for the splines, but you don't really have it here. So I think it's more practical to talk about absolute error. Because, to some extent, if the value itself is really small, then maybe even you have if you have a high percentage error, practically speaking, it may not be too important. Okay, so yes, so important point I want to make here is that for PySR, just because of the far smaller number of terms, it'd be much faster to evaluate these expressions than to try and evaluate the 700 hidden variables in your two hidden layer neural network. And so I think one interesting point I wanted to bring up over here is that very often for PySR, people talk about it as trying to get interpretable expressions. So we talk about interpretability. That's the point of this. We kind of flip this method on its head a bit because we are not really searching for expressions we can interpret from PySR. In a way, we kind of already know what forms we are looking at, right, from the earlier analysis. Instead, what we are using PySR for is sparsity, for a much faster forward evaluation. And I wanted to say that actually, in a way, this is sort of, I would say, a lesser discussed advantage of actually using PySR as compared to, I guess, a neural network. Is that by its very nature, PySR is really designed to optimize for sparsity. In comparison, neural networks, they are not very good at being sparse. I know there is research on sparse neural networks, but in general, you are expecting lots of hidden variables when you are doing NNs. And of course, the fact that PySR, you get visible expressions, it makes it much easier to leverage a priori knowledge compared to the black box model of NNs. So again, for many of you who do use PySR, and for that matter, neural networks as well, I think that's an interesting thing I will actually follow up and discuss with you all about. But okay, so everything I showed before, so we are in the last part of my presentation. Everything I showed before is just for a single layer atmosphere. However, realistically, we usually want to stratify the atmosphere into multiple layers. So there's a nice schematic over here to show you how that would look like. And so using the previous work, we have already addressed the source terms, and it is this intra-atmosphere R and T's that still need to be predicted. That our previous work doesn't, so we can get the S very well using everything that I showed, but these R and T are still a bit unknown, unaddressed. And the reason why we would want to stratify the atmosphere, one is realism, of course. The second is because you often want to compute things like heating rates, and that will rely quite a lot on what is happening within the atmosphere, within the clouds, rather than just carrying what is coming up at the top or what is going down at the bottom. So one sort of like easy way out, I will say, is, okay, let's improve what we can improve, which are these S terms. We just use the old method for the intra-atmosphere R's and T's, which are much easier to try and determine. So some results over here, let's say we try that. And so over here, what I'm doing is that I'm using a realistic, and realistic, of course, by its nature, is a multi-layer cloud. And so in this case, you can see that if I set a low zenith angle, the errors are reduced quite a bit. So the blue is my new methods, the orange is the old status quo methods. But the problem is that in some cases, improving just one part of the model will actually result in worse error. So this is really just a result of compensating errors. And I have tried, if you can indeed determine the perfect intra-atmosphere R's and T's, you would actually have perfect error everywhere. I've tested, just as a sanity check. But the two big takeaways is one, that the accuracy of various two-stream methods is case dependent. It's nothing new or interesting over here because this has kind of always been the case. And if you're wondering like what method is put into, say, CESM, for example, it is actually a method that works really, really well for clouds, and it's well known that it works poorly for, say, for example, Arctic aerosols. But what people think and say is that clouds are the things that we want to get right. So we just use a method that's really good for clouds, even if it's terrible in some other cases. So in a way, this is sort of fundamental, but we are still hoping to make our model more accurate everywhere by trying to determine the intra-atmosphere R's and T's more accurately. And in fact, I have already been working on this for months. This is not a surprise. And we do have some methods to do that, though for time constraints, I will not go into that. Final thing to say on just that first part is to say that the data that we use to test our model on is really important as well, right? Because we cannot comprehensively say that our method works better everywhere, but we will want to show that it works better for the things that we are interested in, usually clouds and aerosols. And yeah, that is all from me. Any questions? Thank you.
Thanks for the presentation. I was wondering if you can kind of mix the two approaches of neural networks and symbolic regression by, once a neural network is trained, integrating it in the library of symbolic functions you're searching on. Is that an approach that can be used?
Okay. Oh, okay. I've heard a similar idea from Jatan, actually. He's not here, but yeah, where you train a neural network first and you use the neural network outputs to train your PySR algorithm. He tells me that it works much better because you sort of like smooth out the data. But is that kind of the idea you're getting at?
Yeah, probably.
Yeah. So I guess I have it on. I am told that that works better. Don't quite know why, but maybe, I guess in our case. But I think in that case, people are working with expression. You're working in a case where they know less about the true form of the expressions. So you might want to do things like that, and you might have noise that you have to deal with, right? Whereas we are dealing with syntactic data. In my case, I think PySR on its own is already works much better than in the typical case because we do know quite a bit about the true expressions.
Thanks.
Great talk, Dan. I'm wondering, how did you arrive at 80 for max complexity? Did you test a bunch of different numbers or you just chose that end?
So I did test for many different numbers, but I think an interesting point to make here is that I believe that I can actually scale up the max complexity even more and get even less accuracy. So in a way, there's a trade-off between complexity and accuracy, as you might expect. And I guess 80 is pseudo-arbitrary in a way. So in a way, I guess it depends on what sort of errors you want to bring it down to. I guess I can't just stop at 80. Also, the training time increases exponentially with your complexity, so that's a consideration too.
Hello? Oh, yeah. So just one small comment on what we had before this question regarding using, I guess, some of the symbolic regression on top of the neural networks.
Yeah.
Maybe from what Jitan proposed or said, I know that there is kind of a technique proposed as an interpretable AI technique, which basically builds a symbolic regression emulator of a neural network. So I know that this has been sort of explored and proposed. In case you're interested, I can show you through the paper.
Okay. Yeah, thank you.
But besides that, I think like one question that I had is because you said we have a lot of knowledge also about the problem or the dynamics. Were you able to introduce this somehow into the PySR? Are there certain physical constraints that you were not able or you are interested in getting into the symbolic regression algorithms?
Thank you for that question. Great question. So to answer you, yes. In PySR, just by the library of forms, I have actually imposed certain. Oh wait, sorry, that's PySR. Oh, okay, sorry. I correct myself. Let me think. Okay, in PySR, I would say that the constraints are sort of soft constraints in the sense that just by transforming my data a bit, I try and push it towards fulfilling certain constraints. If we are talking symbolic regression in general, so not genetic programming, which is PySR, but using sparse regression, in that case, I can impose the constraints quite easily by just choosing my library of forms. And actually, that is the approach I'm sort of inclined to. So I actually do hope for sparse regression to replace PySR. PySR is just a bit exploratory.
So they use Cindy, something like Cindy?
Well, Cindy is optimized for learning the dynamics of ODEs. I don't need something quite so complicated. So I actually do have my own sparse regression. So yeah, my own sparse regression code that I've been using.
Okay, thanks so much.
Hello. Good presentation. I have a very basic question. It's about currently, because in the modeling simulation, the cloud is one of the key points that needs to solve because some model cannot well resolve the cloud effect. So in your simulations, I have two questions. The first is which data set you use? You use the observation data set of cloud or you use the model result? The second question is, can you give me a reason why a higher resolution cloud simulation is needed?
Oh, okay. Sorry, one clarification on your second question.
The first is the data set. Yeah.
I just wanted to clarify what sort of resolution are you talking about? You're talking about vertical stratification? Are you talking about angular resolution? What kind of resolution?
So for your training, for your training your method, so which data set you use for the training, the model result or the observation?
Okay. So for your first question, we are using synthetic data. So it's actually the outputs of my high angular resolution model, die sort For those of you in the know, that is what I'm trying to match. That's my ground truth. So it's synthetic data, not observational.
Okay, so does this model can have a well resolve the reality of the cloud?
Kind of, also not quite. So we are still stuck in the 1D plane parallel framework. So if you want something that is much closer to reality, you need to use a 3D result. But for, I always say various reasons. I mean, this is independent column model, right? Because of that, I guess we consider the multi-angle but 1D solver to kind of be good enough in a way.
Okay, thank you.
I guess in general, if we can get die-sort results using the two-stream, we are sufficiently happy. We don't even want to think about 3D yet.
Thank you.
My next project though, anyway, that's a separate.